Welcome all to the lecture 4, session 2. Hope I am audible. Can anybody please confirm that I am audible? Am I audible? Thank you very much. Okay, so let us start the next thing that we were doing, and it is a very important thing. I told you one thing that most of the time into the AI domain, whenever we are going to solve the problem, the number of states are very large, and they are pretty going to be near about infinite. And if we start doing, because we know the branching factor, because if you are here, we know that there are finitely many possibilities that you can explore. So that is finite, but when you explore the finite to again finite, it becomes exponential, and it goes towards the kind of infinite. It's become infinite. So therefore, the time requirement becomes b to the power l. It means time requirement becomes infinite, and therefore DFS you cannot apply onto those scenarios. You cannot apply DFS because if you start applying DFS, it becomes, sometime it may be possible that it becomes that you traverse all the things, then only you are able to return. So therefore DFS cannot work. So one improvement into the algorithm is this, that you apply depth limited search. You say that only I would go into the depth trend only, and if the item is not being found out till the item is not there. Okay, so if you apply like this and your branching factor is b, in every state you are telling b, so how many items you have, b to the l number of items. So therefore those many number of times, though this much number of time is would be required. So time complexity is b to the power l, order of b to the power l. Is it clear? Okay. And what is the space complexity, or how much space is required? B multiplied by L, because at every step when you came down, you are putting B item in one path, because when you are at the extreme depth, the maximum number item needed when you are at the extreme depth. And every place there are B possibilities. So all those things would be into the frontier. Everything would not be into the frontier. Okay, when you started from the place, you put all these things which are there into the frontier. You go to the next, you put the nearby things into the frontier. Okay, are you able to see this? See this. Okay, let me just see. Let me plot it. Just assume this condition that this is the scenario. Okay, let's be 1, 2, 3, 4. Let's assume 1, 2, okay, 3, 4. So what would happen in the frontier? What is there? 1, 2, 3, 4. So here I am telling b is equal to 4. Branching factor is 4. So initially what would happen, that in your frontier how many items would be there? Because although I have not explored that 4 items are there, 4 items are there, 4 items are there. Everywhere there are 4 items. Okay, 4 items are there. So which item I am going to put into the frontier? This had been explored. Okay, this item, when I came here, I had explored this. When I explored this, I would be putting these items into the frontier. 1, 2, 3. So 1, 2, and 3 would be into the frontier. When I come here, I would be putting these items. Say 4, 5, 6. These items 4, 5, and 6 items. These items I am going to put. So these are the 3 items. These are again the 3 items I am going to put over there. Okay. So when I come here again, I have put those things. Then I would explore here and put over there. So at the extreme end, when I am there, how many items are there? These many numbers are at every level. How many levels we have? If I am going to L, to L minus 1 places, everywhere there is B minus 1 item. Are you able to see this? What it is? L into B minus some combination of minus L. It is what it is? LB minus L minus B plus 1. So these are the small numbers. Therefore, I will be taking only a bigger number, L into B. So these many number item would be into the LB order of LB number of item would be there, because it's only the dominating factor. So why it is a good concept? Because it saves your space. And what is the diameter? Sometime if you have a graph, so you can say that, because these things are actually going to be connected. Now, let's assume this is connected to there, this is connected to there. So you find out that because of these connections, there is a maximum distance between two nodes. Let's assume that it is from this node to this node, and this is called the diameter. Okay. question, there is a question that B value may be vary at different level or would be same at all the levels. My answer is that B is the maximum branching factor. That would be fixed, but it may be possible that some places there would be less item. There would be less items, but B is fixed number because it's a maximum number. Okay, that's it. Okay, चलते हैं. Okay. So we understood the idea is going if you go beyond the diameter, because if you have a graph, there is a diameter. If you go beyond the diameter, it's useless because you say that there is infinite item. It's not a good idea. Same algorithm is there, that how you are going to do this thing. You try to find out that what is the depth, and if the depth is greater than something, then you stop. Okay. So then again a new problem comes. What is the new problem? That since you are going to tell I'm only going to consider the 10 limit, then there is a problem that it may be possible that your solution is not available. Okay, it may be possible that your solution is not available into that particular place. Then what would happen? You would be into the problem because you say that I am going to only take test 10 items, but 10 up to 10 depth, but your goal is not available over there. So you would be going to give the wrong answer. Okay, you would be telling that I am failed, but our question is there. Then how to come out of this? The idea is iterative deepening. Iterative deepening. What is iterative deepening? That you initially start the depth limited search with the 0, then 1, then 2, and so on. You keep until you find out your goal. Is it a good idea? You start with the iterative deepening algorithm you apply means you apply DFS and you would not go beyond the L depth, but you are increasing this depth. So what you are going to do? Are you able to see this algorithm? The algorithm is this. That this algorithm says that you have. Let's assume that you have a tree, and I am telling that I would not go beyond this particular depth, that is L. Okay. So what you would do initially, L was 0, then L was 1, then L was 2, and so on, until you find out the solution or goal state. Okay. So what is the problem with this thing? That this is better idea, no? Because earlier I was telling that I'm only going to L is equal to 10. So here by 10, if you don't find the answer, this algorithm also tries L is equal to 11, because this algorithm would not stop. So one by one it is trying everything. Okay. So therefore this iterative deepening is going to give you the answer. Earlier was not. It may be possible that it may fail. Okay, very simple idea that you are increasing this, but there is again an issue. What is the issue? The issue is this, that when you, for example, when you are going to for the L is equal to 5, and when you are L is equal to 4, so you have explored all those things, okay, and you have seen that the answer is not available. But when you apply L is equal to 5, you would be considering all these items, and you are applying the DFS. So when you apply DFS over here, and when you apply the DFS over here, these items are actually common. These items are common. So you are actually again considering these items, and these items are, and you know that there is no solution for these items. Here there is no solution. You see that there is a problem. Can you identify this problem? Can you see this? Can anybody write yes? Can you see the problem? No, otherwise I would explain. Okay, you see this problem, na? If I say that I am going to consider the level 4 item up to level 4, so these item I am going to consider, but I have not find out the answer. Therefore, I would increase the level. Level is equal to 5. Then I would consider these item. The issue is when I was considering, when I was working for the L is equal to 5, I have also considered these item again, and I know that there is no answer. Why I am repeating this consideration? So this is the problem, and however this seems to be a valid issue, but actually this is not a big issue. Okay, that we would be seeing. Okay, So I told you the issue. So, and this is the algorithm, you know that. You increase the value of L from 0, 1, 2, 3 and so on until you find out the goal. Memory requirement is B multiplied by D. You understand that what is D? D is the depth at which you find out the solution. So B multiplied by D. Okay, this is what the memory requirement you have, because those many items need to be stored into the memory to find out the solution. Okay. This is the point that I wanted to raise. The iterative generation of the same state seems wasteful, but it is not, as because most of the nodes are at the leaf. Very important thing is this. Very important thing is this observation that most of the nodes are at the leaf. Try hybrid if needed. What I mean by this, that very important concept, that this tells that I told you that you cannot apply DFS. Why you cannot apply DFS? Because your things are infinite. Your things are infinite. Okay, so it is the actual value goes to infinite. Okay, and whenever, let's assume you find out the answer at the depth D. Okay, let's assume you find out the answer at the depth. What is the depth? At the depth D. Okay, then just consider the item which are inside this. What are item inside this, and compare them which are the items which are here. Okay, since it goes to the infinite, so if you see from the higher perspective, it looks like this, that this is only a smaller portion, very small portion, because only this, whatever item you have, they are finite, they are very small, and it's a open-ended item. Therefore, these items are, whatever item here are, they are very negligible as compared to this infinite. This is infinite space, because this is the infinite space. Understand? So although you are considering the multiple number of time, but the item here are actually very large, and therefore into the real applications it is not going to be difficult, because you are going to apply this algorithm into the places when you cannot apply DFS, and for those cases definitely this is going to work. Okay, the time complexity is this B to the power D, because you have to consider all the items which are up to there, and they are B to the D items. And you know the memory requirement, as I earlier told you, that it is B multiplied by D. We have seen there. Same algorithm. Depth is from 0 to infinite. You keep doing things until you find out the answer. Okay. Can you please give one example to visualize the finite and infinite here? Is it clear? I think you have answered the question. What is finite and infinite? I think this particular graph explains this. This is the infinite thing. So in this infinite depth, you see that in this infinite this items are infinite over here, and here the items are finite. Is it clear now? Real time example. Look, real examples. You consider what is infinite. First, you understand what is infinite. Infinite is something that you cannot represent. Okay, you cannot, your system, if you have the capacity to eat 10 chapatis, if I give you 20 chapatis to eat, it's infinite for you, because you cannot eat them. It becomes infinite. Even if I give you 1 lakh chapatis, that is also infinite for you, and if I give you 20 chapatis, it is also infinite. Infinite means sufficient. It is greater than that thing. Okay, so these things are going to be very large, because you are not going to consider them. Okay, these things are going to be very large, because it's a every layer there are D number of items. Okay, every layer, if here the items are only 2 to the power D, but if I say that if I just show you that what is going to happen, let's assume only D is next to there, instead of infinite there it's only D. So how many items are there into the tree? It is 2 to the power 2D. Okay, how many items are there into this tree? 2 to the power D. What is the difference? How many items are there? It is 2 to the power 2D minus D. It is 2 to the power D multiplied by, what is this number? What is this number? Can you read 2 to the power D minus 1? 2 to the power D minus 1. And 2 to the power D minus 1, how much it is? It is 2 to the power D. Nearly, because 2 to the power D is only. And here the value is 2 to the power D. You see 2 to the power 2D. Means all the items are here only. Looks like, because if I say, if you agree by this, that 2 to the power D minus 1 is 2 to the power D, if you agree with this concept, then you can say that nearly all the items are there, only very small number of items are there. This is what we mean by the infinite. Okay, and okay, Then somebody is asking very valid question, what it mean by the hybrid. I told you that then you should try the hybrid example. This is written over here, that in case you see that there is a problem, then you can go ahead with the hybrid approaches. What is the hybrid approaches? Hybrid approaches means you can say that you put color on some of the nodes, and when you put color on the nodes, you need not to put those nodes into the place. Okay, so then you are not going to consider them for the testing that whether it is a goal node or not. Whenever you seeing a node, you are just skimming them and you are not putting them into the frontier, because you know that I need not to apply some of the operations over there. The hybrid approach means, because in this approach I'm telling that you are not applying any concept that item which are traversed I am not going to consider, but in the hybrid approach you maintain something by which you can do these operations. Is it clear? Iterative deepening, one by one you are increasing the level of the DFS so that you can apply the DFS, and the place where you find out the answer you stop and give the answer. This is what the iterative deepening. Okay, so this is again the same algorithm. I think it's clear to you, and yeah, I think you are with me with the time and space complexity, and if you are not, please see the earlier algorithm or I'll ask the questions. Then this is a very important concept. This is again a new kind of searching algorithm that is called the bidirectional search algorithm. It tells that what is mean by bidirectional search algorithm. It is like that. Let's assume that there is let's assume that we have we have a graph. We have all these nodes which are connected, and I tell you that you are into this state, and I tell you that you have to reach to this state. Okay, so you are actually the general strategy that you follow is that you keep expanding from this point, and you keep expanding this point until you reach over there, and then you say that okay, from this particular thing I have since came from this thing, and this is the path, this is the solution. This is how you go ahead. But instead of this, you can do altogether different strategy. What is that strategy? The strategy is this, that you say that I'm told to start from here, I'm told to reach over this point. So let's assume if I expand over here, then where I'm going to reach. Okay, so let's assume somewhere you are here in the middle, and you also start spending from this point also. So if you start spending from this point, so at some point it touches. So if you start from both the sides and you somehow decide, okay, oh, I got a junction point, then at this particular moment you can find out the path. Okay, this is the path. Okay, what is the advantage? You see, very important thing, that earlier this was the depth. Okay, earlier this was the depth. This was from here to here. Okay, the depth was from here to here. But in this case, you see that the first part goes to the depth d by 2 only. How much effort is required? Okay, let's assume if its branching factor is b, it is a b to the power d minus d by 2. And the same effort is also needed to be applied from the second side. So therefore you say the total effort required is b to the power d by 2. So it comes out to be b to the power, because you can find out the summation, 2 multiplied by b to the power d by 2. This is what the things. And 2 is not important because 2 is a constant thing. So in terms of the order, you say you are going to spend b to the power d by 2 only effort. Order of this effort you are going to apply. But earlier, if you have not gone through this mechanism, you have to traverse from here to here, and therefore your effort was b to the power d by 2. I just compare, b to the power d. I'm sorry, b to the power d. Earlier your effort is b to the power d, and b to the power d is very large. Okay, if you compare b to the power d and b to the power d by 2, they are a very large number. So therefore you say very much improvement. Sir, somebody is asking, sir, please explain bidirectional search again. Okay, so I'm once again explaining all these things. I'm going to delete this thing. Any questions you have? Okay, Here I'm going to delete this thing. I'm once again explaining what is mean. Assume first. Please let me know that you are with me. Okay. Whenever you ask the question, I'm answering you. Assume that this is all the space, means there is some graph is there. Okay. I tell you, you start from this point and you reach to this point. Are you with me? Are you with me? Can you write yes? Okay. So what you do from here, you start expanding yourself because it's a DFS now. So you see that I am expanding this way, and also simultaneously you start expanding from this place also because you also apply start DFS over there. Somewhere you find, okay, I got a point that is into the both the places. If you find out such a such a place which is into the both the place, then what you can do, you can now discover that this is the path to reach from here to here. Is it clear? Okay, is it clear? If you find out such a, you find out this thing. So what is the depth from here to here? What is this here to here depth? Depth is D. Okay. How much effort is required? Branching factor to the power D. This much effort, order of this much effort is required to find out. If you find out the solution, if you find out solution using this thing and exploding this thing, this much effort is required. This would require how much effort? This would require how much effort? Order of B to the power D. Okay. But how much effort this is going to take to come from here to here only, and this would take order of B to the power D by 2. This second part is also going to be order of B to the power D by 2. And if you find out the summation, it is 2 multiplied by B to the power D by 2. So in the order notation, you know that this is not important. The constants are not important. So what is the gain? Exponential gain. From the B to the power, if somebody was telling you, give me 2 to the power 20 rupees, and I ask, and somebody asks, give me only 2 to the power 10 rupees, it's an infinite time gain. Okay, just see what is the comparison. Can anybody find? This 2 to the power 20 is 2 to the power 10 multiplied by 2 to the power 10. Means this was 1 rupee and this was 2 to the power 10 rupees. A big thing, big difference. So this is what this algorithm is. It says that you start from both the places, both the sides, and somewhere you find out that there is a middle point, and using expected searching time is to B to the power D by 2 D by 2. That is much less than B to the power D. If a problem, the simple example see there, but sir, but every time we will compare the status here, right? States here, we will compare the, yes, we would compare the state. So that is not difficult because you can put every color, if it's different color, whether it is there or whether it is into the second thing or not. You just put the color, okay? Because whenever you are visiting something, you are having colors. You maintain by using colors. So color could be white, gray, and black. And if you find anything. And white, black, and gray. So from the start place, you say that either the color is white, gray, or black, and from the goal state, you say whether it is a white, pink, or red. Okay. So from the pink side, if you find something that has a color that has a color say black, then you say that okay, this is the place where we can merge. Okay, go ahead. That's not difficult. Okay, so see this example. If a problem has a solution at the depth 6, means you see that from here to here at the depth 6 there is a solution. Okay, at each direction, and each direction run the BFS or DFS, whatever you want, and the search meets at the depth 3, and the search meets at the this 3. For branching factor is equal to 10. Branching factor is equal to 10. Total number of nodes generated is 2220, because one side if you go down, every place you are 10 at the place 10, then 100, then 1000. So 1000 plus 100 plus 10 becomes this 1110, and therefore since both the sides it has been generated, if you find out the summation becomes 2220. So these many number nodes are generated. But if you apply only this single side BFS, it is going to be 111110. See how many different nodes are there. You find out this, okay? Bidirectional search, very important example, and this is a very important application. Are you with me? Everybody understood this? Okay. Okay. Everybody with me? Any questions? No? Is it clear? Sir, I think there is a question. Please write down the question. Okay. Are you with me? Okay. So somebody is calling how 2220 came. So that is start. Just take these things. How 2222 came. Okay. See this thing. This is what we have. Okay, na? Control A, delete, Control V. Okay. See this. See the things. Okay. Let me give the problem. Somebody is asking why this value came. Okay. Control X, Control A, delete, Control V. Okay. So let us see that how this value comes. Okay. Just let me tell you how this value comes. Okay. So what is the problem? That for B branching factor 10 means what? If you have a node, then how many other nodes are there? Tell me. Branching factor is 10. How many other nodes are there? How many nodes are there? 10. So how many nodes is there? 10 nodes is there. Then since there is again branching factor, then it would be exploring all those things. So how many nodes would be there at this level? 100. Are you with me? In the third layer again, these many number of items are there. How many items there? 1 0 0 0 items are there. So up to 3 level, if you generate all the items, how many items you have generated? 1 1 1 0. These many number of items you have generated. And since you are also doing the same thing from the solution from the goal state, so at the goal state, how many nodes are there? 10. Above that, how many nodes are there? It is 100. Above that, how many nodes are there? 1000. Total, how many items are there? 1110. If you find out the summation, how many total number of items you have generated? This. Is it clear? Are you with me? And if you have done this alone up to 6th state, how many nodes you have generated? Can give me the answer. Can you write this? If you have, because this was also be one of the states over there. Now, if you keep explaining into this way, how many nodes have been till now generated? Can anybody write? If you had gone into this way only, into the next step, number of item would be 1 1 1 0 0 0. This many number of item. Into the next level, item would be 1 0 0 0 0 0. You keep like this. How many items would be 1 1 1 0? Okay, 1 1 1. This many number of items are there. Is it clear? Correct. Right. Okay. Okay. Fine. Great. So this table actually try to compare all these things, and I think that should not be difficult for you. Just go through this. A search study is complete if it can find a solution, if it is there. Okay. If the solution is there, it can find. Okay. BFS, best first search, is complete because one layer, second layer, third layer, it keep progressing, and therefore it can find out. Uniform cast, it can find out because uniform cast, because it can explore one by one items, and therefore it can find out. DFS cannot find out the solution if infinite number of, if depth is infinite, then if depth is very large, it cannot find out the solution because in one place it can be stuck and it cannot give you the answer. Depth limited. Okay, depth limited. If you say that I am only limiting only 10 places, no, you cannot give the answer because if answer is not there, even if there is answer, but you are only considering 10 things, you cannot give the answer. Iterative deepening, yes, because now you are increasing until you find out the solution. Bidirectional, yes, you can find out the solution. Okay, it's complete. So the search is complete if it can give you the solution. Are you with me? Everybody understand this thing? Is it optimal? Whether it gives the optimal solution? Yes, yes, yes. Everywhere, whenever the solution is produced, it's an optimal solution because you can backtrack and give the right answer. And when you cannot produce, then there is no point of asking this question. Okay. What is the time and space complexity? You see that for BFS, B to the power D. All these things we have discussed. Okay. So I'm not going into the detail. In BFS, it is not optimal. Right? No, it's optimal because when you have find out the solution, then you would generate the things by backtracking. Then it becomes optimal. BFS and DFS only tells what is the order in which you are considering the item. But when the item has been considered, then you generate the item using the back propagation. And back propagation is, I'm using a different kind of word, but you backtrack by backtracking. Okay. So therefore you give the answer, and that answer is optimal. Okay, are you with me? There are two different things. finding the answer in which order. It may be possible that it is not giving the answer into the right order, but when it gives you the answer, it may take longer time, but when it gives the answer is optimal. Okay. Best algorithm means in terms of time it may not be good, but in terms of the solution, your solution is optimal. So any more questions? I think this particular slide should be clear. Next algorithm we are going to see. Okay. Now we are going to see the informed search. Okay. And informed search means you have some more information, extra information is available with you, and that information we are going to call as a heuristic function. It means some heuristic function is given to you, that is that takes a node as input and output the what is the things over there. So some more information is also given to you, okay, and that you are going to utilize. So so we are going to see first the greedy best first search. Greedy best first search. What is a greedy best first search? Means the extra information that is given to you, this algorithm uses that thing to explore what to explore next. So ultimately we want to find out some strategy that when the items are given to me, what is the best order? So what order it is going to follow? This algorithm, greedy best first search algorithm, what order it is going to follow? It is going to follow the order that has been inspired by the heuristic function that it has, extra information that it has. Okay. So if you are at the goal, then your heuristic function is 0. Otherwise, the heuristic function has some value. So you want to find out the place so that your function gives you the smaller value. Expand the node that is closest to the goal. This is what the simple one-line explanation. So if somebody gives you, for example, see this example, I think it will be clear now. It will be clear to you. For example, let straight line distances to the Bucharest is known. What do I mean? Let me go back. So this is the graph, okay? Bucharest. If a straight line distances are given, means Figueres, what is the distance? 211. From Cebu, what is the straight line distance? So if somebody gives you extra information, means from here to here, what is the air distance? From Piteres, distance would be 101, but from the Rimunu, the distance would be different. For Niement, the distance would be this distance. So if somebody give you this distance, so for Niement, the distance is 87, 72, 142, 85, then only if you find out the summation, then only you can read. But if somebody gives you Niement to Bucharest, the distance is, somebody gives you like this. Niement, what is the Niement 234. If somebody give you this information, then can you utilize this information for better exploration? Okay. So yes, we can utilize. If we utilize this information, then we are going to we would say that we are having the greedy best first search. Okay, greedy best first search. We are going to see the best thing first, and that is dependent upon the extra information that we have. Okay, so let us see an example. So initially you are into the Arad. That is given 366 kilometers by this information. So you see 366. Here you explain that what is the possibilities. You see the map from the Arad, CGU and Tamisha and Zamet. These are the 3 places that you can go. So you just I told you that you take the printout of this thing, print a screen of this thing to find out the solution. So you see that you can go at the 3 places, and if you see the distance from the goal state from Cebu, so you see that where the Cebu, can you find out? Cebu, what is the distance? Cebu, 253, so this is 253. Timusia, so you see what is the distance, so this is Timusia 239, so 239 is there, then 374, so which is the smaller? The smaller is 253, Cebu. So you from Arad to you go Cebu, then you explain this Cebu. From Cebu you see first you go and consult the graph. There you find out what are the nearby. You write all those places and you write their distances because you know the distances are given here. This is your extra information. You put Arad, you can go to the Arad, you can go to the Figueres or RDA, and you go to these places, you put the distances because they are given, then you find out the smallest one is Figueres. Then you expand the Figueres and you find out that there is a pace to directly to the Bucharest, and that gives you 0, and therefore you find out this space. Please note two things. What are the nodes that you have explored? You explored this, but what is the part? The A to here, A to here, A to here, and A to here. So although you find out them, you explain, but sometimes you may have explored something that is not part of the path. This you should know. So you understand the greedy base first search. I think it is a simple search, and that is based on the extra information that is given to you. So who gave you this information? I'm not talking about this. Let's assume that somebody has given you this information. If this information is given to you, so you can go ahead in this way. Are you with me? Given this information, can you find out this tree? Are you with me? Can anybody write yes, or you ask the question? If you have any doubt, please let me know. Are you with me? Okay, I got yes, and that's pretty straightforward. No, there is no magic in this. You just see the first node because you start from the array, and then you see that what are the places nearby. You have seen that this graph, Sidhu, Timisi, and Jamal. Dekho, from the array, the 3 places are Jerin, Cebu, and Tamusia. For these places, you know that what is the air distance that is given to you, and you use that. You put this 253, 329, and 374. And then the minimum is Cebu. Then you expand the Cebu. You see that from the Cebu you find out the Valkia and Figueres, and you from here also you know what is the smallest distance. So here you expand the from Figueres to from smallest distance from Cebu you Figueres, and from Figueres you find out the Sibia and Bucharest, and you find out the solution. So I think that's pretty straightforward. Next algorithm is a very important algorithm, and you would be very happy to see this algorithm because first time we are going to have a very good kind of algorithms over here. All those things are also because they are discussing a different perspective, but this is an altogether new kind of algorithm. And this actually tells nothing bigger concept. Concept is very small. It tells that you know the path cost now. What is the cost of the path? That is GN. You know, you find out if you are at some place, how much cost you have incurred to reach to that place. That is GN. You find out now. You know this GN function, and you know this HN function. What is HN? Is the heuristic function. Okay, HN means these values are actually HN. They are the extra information given to you. And what is GN? GN, if you are here, Cebu, so the value would be from Arad to Cebu, this is 140. If you go Figueres, so this 199. So for Figueres, the value would be 140 plus 99. So this is the distance, how much you have spent when you reach to that particular point. The two things, na? Earlier means you know that if you are Figueres, you know that what is the distance you have spent, and then you know the air distance. So the summation would be like that. Okay. So two parts are there. First, that how much you have spent. So for the root node, GN would be 0, but HN would be having some larger value. So if you use this particular summation, means the GN plus HN, and use that thing as a deciding factor, which will be, and then because now you are going to consider again every time we are going to talk this only, that what should be the order of items we are going to consider. If you are using that thing as a giving you the order, then this particular search is called the A star search. Okay, we call it A star search. And this particular algorithm is both optimal and complete. Optimal means give you the right good answer, means the smallest answer, and the complete means if answer is there, it would be able to provide you that answer. It expands the node in order of increasing F value. So initially F value would be small, but F value is going to increase because you are expanding the things, and increasing F value, if you are going to apply this, you are going to get the right answer. Very important line is this: no other optimal algorithm is guaranteed to expand fewer nodes than A star. Okay. Somebody is asking what is GN. Okay. So I just want to ask that, do you know what is HN? You write yes. Heuristic. This is the information, because I told you that somebody has provided me this information. This is what the heuristic H function. Okay, H function is this. I told you many other time. I'm telling that heuristic function is something, some other information that is given to you. For every node, some information, value is given to you. Means given the node, can you give me this value? This is what the heuristic function. Are you with me? Everybody with me? That you understand what is the heuristic function? Correct? This part you understand? Everybody understand HX, HN? Yes? Very good. Now I am going to tell you what is GN. I went there and I also explained just now. एक बार फिर से बताता हूँ. Once again I am telling. If you are here, you want to find out GN. It is, you started from array. So for this GN for this thing would be 10118 plus 111. For this place, you find out the summation of all these things. For this place, you find out the summation of all these things. Means how much you have expended to reach at this particular place. This is what this GN. Okay, understand? This GN. How to find out how much you have expended. And this second thing is a magical information. That is heuristic. That is extra information given to you. You got it? Thank you. So if I am going to use this summation, then it is called the A star stress. Okay, very important line. No other optimal algorithm is guaranteed to expand fewer nodes than A star. We cannot, the other algorithm you cannot give a guarantee. Means I would be giving guarantee. It may be possible that carefully selected example can give you the smaller number of steps, but you cannot guarantee. Means in all the cases your algorithm is going to be better. In some cases your algorithm would be better, some cases A star would be better, but but most of the no, I cannot say like that. But you cannot say that every time your algorithm would be better. That you cannot say. Okay, means it's going to be a good algorithm. Okay, so how this algorithm works, I think, I'm sorry for that. I think this value is very small, and you cannot. It is difficult to, looks like they're difficult to read on this screen. Can you read this? Okay, can everybody understand that what is written over there? A star. I think you should not much worried about this, because by yourself you can work on this. For the array, what should be the value? Value should be 366 plus 0. Because why 366? Because array, for the array, I think you see the air distance from the array is how much air distance is. Can anybody see? Array 366. Okay. So therefore, when you start from array, 366 plus 0, because this the G part, that is how much expended you, is 0. And then you from array you expend the 3 places, and for those 3 places you find out the how much you are spending, and how much you are spending you can see from this graph. That is from array you find out 3 places: Jarind, Cebu and Tamosha. So 118, 180. So let me just write down this. Okay, let me just give you this 1 or 2 things so that it becomes easy for you. So this is the graph now. You start from this place. You start from this place. Okay. So H value, you know that earlier we have discussed that what is the value of H. Let me just see that what is the value of H. Okay. So for ARAD, the H value is, can anybody tell that what is the H value is? Previous slide it was there, 366. And for Cebu, it is for 253, and for Jarind, it is 374. For the Tamasya, it is 329. Okay, so what is the, you got the G, you got this H values. What is the G value? G value you know, because G value is 140. To come here, because you started from this node, the G value is this plus 140, and here G value plus 175, because here is a 75 now. For this thing, 329 plus 118. So you find out these 3 places. What is the summation? Can anybody give me what is the summation? Summation seems to be, it is 9,499. Am I right? Please check. 393, and this is going to be 447. Okay. Am I right? Okay. So which is the smallest one? I think Cebu is the smallest one. This is the smallest one. So you from Arad you go to the Cebu. because this is the smallest one. Okay, then you go to the next thing. Okay, is it clear? Is it clear? From here also you can find out. From here where to go? Again you apply the same thing. You find out Figueres, what is the value? What is the Figueres is 176. Figueres is 176. I think I should take one this value 176, and well it is 193 because distance is, air distance is reducing. So what you have to add? You have to add this thing is 140 plus 99. 140 plus 99 because here you have to spend this much. This place you have to add 140 plus 80. You find out what is the summation, whatever be the minimum value, you are then from here you would go into that direction, and you keep going, and then at the end you would be finding the solution. So I think in this graph you can one by one expand this. So from Arad you go to Cebu. The same thing. This all the values are summation written over here. It is written in the book also. I taken from the book itself. So you can. Are you with me? You can find out in this way and see that how the things are expanded here. Can you do this? Yes, everybody. So it's a experiment. It's a homework for you. You please go and solve by yourself so that you can go ahead and you can solve this particular problem. And let me tell you a very important thing that is very important to tell at this particular moment, that all these things that I'm going to tell, when they are going to apply, this means I'm going to tell you one thing now, biggest thing I'm telling, there is no other optimal algorithm is guaranteed to expand the fewer nodes than A star. When this would happen, there is a special condition that the condition is admissibility and consistency. Okay, the condition is admissibility and the consistency. If these two things are there, then only my algorithm is going to work. So what is the admissibility? Okay, admissibility and consistency. So let me just take this print out. That let me just tell you this particular part. Okay, this function should have two properties. This function should have two properties. One is admissible consistency. Okay, and these things are very easy to see. What is admissible? Admissible means, by admissible I mean that whenever you go from A place B, all the place, you don't overestimate the things. Okay, you never overestimate. For example, in our case, we are using the heuristic function. This particular heuristic, this heuristic function should have this property. Okay, this heuristic function should have this property, admissible and consistency. These properties should be with the heuristic function. What are these properties? Admissible means it never overestimate the things. It should give the right information. It should give the right information. What do you mean by right information? Because into the graph we just want to find out the distance, and distance is the distance. And I told you what this information is going to be given to you is the air distance. And air distance comes with a straight line distance. If it is a straight line distance, so it would be a right distance. You cannot tell that. You cannot tweak around it. So these values are admissible. Means they are not overestimating. They are giving the right values to you. Number one. What is consistency? Consistency means that if you are here, you want to go to here, and in between you are at this place and you go at this place. You spended something to come over here, and then you come over here, go from here to here. Okay, from here to here, if you go to reach over this particular point. So the summation, this particular value, okay, and if you add over this particular place, it should be greater than this. It should not be negative. All the values should be positive, and it should only increase. Okay, means h of n is greater than equal to cost of n taking the action and going to n dash plus h of n dash. Okay. If you take the n dash, we call it n dash, we call it node n. If you go from node n and n dash, then the h function that you are going to actually apply on this and this and this, they have the relationship that this should be greater than this. If you add something to get this value, so that it gets decreasing, because as you go, because there is some path cost is associated, it means that it is going to decrease. It is never. There is a consistency, means the value is continuously changing for all the nodes into this path. The value h value is going to decrease one by one. You know, na? Because we are going to talk about. We have talked about this, that it's an air distance. So if whenever you are moving towards the item, your air distance is going to reduce. So these two conditions should be there. If we would be discussing this in the next class also. So if these two conditions are there, then your answer is correct. And what is the implication of this thing? Implication of this thing is this, that let's assume, let me just give you this particular graph, and let me show you this. What is the implication of this thing? Implication is this, that what happens that when you start from this point, that when you are here, because of the implication, so when you are here, you are having some value. Okay. The summation of f function, that is a summation of two things g and h. You see that this function has some value. Okay, and if you increase something, if you go some beyond, means if you go here, okay, so you will be getting a different value. Okay, so if I specify, let me just quote rightly. Here the value is actually 380. The summation is 380. Okay, and here is the summation is 400. Okay, let me just and here the summation is 380. If you find out the value of f, okay, it will be 380. And if you find out here, the value is going to be 400. Okay, if you go ahead with this thing, if we go ahead with this thing, I think here the value is 420. So you see the values are actually one by one increasing. Okay, these values are one by one increasing, and you can find out these kind of contours. These things are contour. These things are going to be contours. So in every step, what you do, you are initially into the array, and then you increase from one contour to another. Then because all the values of f are actually same over whatever the states are here, so therefore you would definitely go from here to somewhere else where the value is going to increase. So one by one you are going to increase, and you know what could be the final value, because final value is not infinite, it is maximally bounded for the goal state. So definitely when you start from some value and you keep increasing, and you know that what is the final value, then you would definitely going to converge it, provided that if I say that in every step you are going to at least increase by epsilon. So all these things are important, and we will be discussing in the next class. So that's all for today. Any more questions? So homework is there, that is just a verbal homework, that you go and you try to explore this particular tree, that how A star works, and this is a very important exercise. Then we will be in the next class discussing that why it is optimal algorithm, and why it is guaranteed to spend fewer number of nodes than no other algorithm is guaranteed to explore fewer number of nodes. Correct? Are you with me? Thank you very much. I'm going to stop this. In case you have any question, please let me know.